All right, we're going to talk about pressure distribution, and I'm not going to spend a lot of time telling you how to design them because we've done that before, and most of you have done that in also in your own practice. But I do want to talk about pressure distribution as a benefit because it gives you equal distribution, and we use it with the Verti-Grid, but we also use it in other designs also with other products and materials. The two are not directly related, but we designed this to use pressure distribution because I'm convinced we should be pressure distributing wastewater in every system if we want to get a good length of life, a good longevity out of our systems. And that's why I say we should design systems that last as long as a house, not just systems that last 20 years. With one replacement area, so that's 40 years. So if it goes as predicted, in 40 years you run out of systems, and you start going back and digging up and redoing the old systems. So anyway, examples, sand mounds. This is a large sand filter in another state down south, but it's equal distribution using small diameter pipe and lots of pump capacity. Geotextile filters, those of you that have been around know this is the Advantex geotextile filter that Renko makes. That's pressure distribution to the nth degree because they've got an orifice about every 6 inches across the top of those filters. So that's how you shrink the size of the treatment unit down to a 3 by 7 or 8 foot pod is by distributing the wastewater equally over the entire system and using a media below that maintains aerobic conditions. This is pressure distribution in standard trenches with stone. This is a system we did 30, 40 years ago. A large system in Oakland County where we used some hydraulic sequencing valves, but we used pressure distribution to spread the wastewater, treated wastewater over a large soil absorption system. So we use the same thing with Verti-Grid. So now we use Verti-Grid, we distribute the whole system, we design it and lay it out, and this product is designed as long as you follow the limits of the procedures recommended by us to use this product, you get equal distribution throughout the system to the degree of each of the pods get an equal amount of water every time the pump kicks on. So pressure distribution uses the whole system from the time of day one flush.
How long does the pump normally run per day? Like, we talk about pressure distribution, I'm completely new to the industry.
Well,
does it run for 10 minutes, an hour, or 10 hours a day? Or...
How about a minute at a time? Okay, so let's say you've got a 50-gallon a minute pump feeding a system. And the flow from that house, I could prove it to you, but on the average it's going to be 150 gallons per day per household or less. That's the actual flow. Doesn't mean what you counties require systems to be designed for. They require 6 people per household and all that. So they want to design it for 450. But regardless of that, it's 150 gallons is what you would expect out of an average household in the state. So 150 gallons of a 50-gallon a minute pump runs 3 minutes a day. So
we'll talk a little bit about that after lunch.
Okay.
Yeah.
So okay, put your thinking caps on a minute. And I've used this illustration before, but what has to happen in a septic tank for water when you flush the toilet? How much is the gallon? How many gallons goes out of a toilet these days? Some of you at Valley Farms probably know. About 1.6 gallons is standard. Might be 2.5. I don't know if you've got an old-fashioned toilet. 1.6 gallons is pretty much standard across the board now to be used. 1.6 gallons goes into 1,000 or 1,500 gallon tank. What has to happen in that tank to get any water out the other end? The water level in the tank has to rise by 1.6 gallons. 1.6, the 1,000 gallon tanks is about 20 gallons per inch, Mike, in a 1,000 gallon tank, or Jason? 1,000 gallon tank, 20 gallons per inch. So how much does the water level in that tank rise when you flush a toilet? 1/10 of an inch. If it's a 1,500 gallons, about 25 gallons per inch. So it rises even less. So going out the other end, their water level rose 1/10 of an inch. Going out the other end in that 4-inch pipe coming out here is a trickle flow in a pipe. It's just barely flowing. And how many of these holes does it take in the drain field for that 1.6 gallons to find before it all goes out into the stone? I don't know the magic number, but these are generally 3/8 to 1/2 inch holes in a perforated pipe. And once it finds a hole, all that water could be going out 1 or 2 holes. And there have been some recent tests and demonstrations shown on that actual thing. So how much of that drain field gets used for the first year, or the first 5 years, or 10 years? Next to none, right? So that water, I want to use this illustration. I like it. Okay, so drain fields cost from anywhere 15 or 20,000 up to 60 or 70,000 today, depending on what county you're building in. But anyway, they're expensive. The average cost of repairs in Ingham County, I understand, in 2024 was like 42,000 some construction costs plus design. Okay. Anyway, those are repairs, so they cost more. But anyway, you got a big system. Okay, so you got a big family and you want a big house with 4 or 5 bedrooms. Okay, you move your family into that house, so you spend a lot of money, maybe $500,000 today building a 5-bedroom home. You move everybody into that house and you occupy 1 bedroom. The whole family moves into 1 bedroom. And until you get tired of living with one another, sleeping with one another 24 hours a day, you start, some of your crowd starts moving into other bedrooms, but you save those other bedrooms for the rest of the. Does that make any sense? It doesn't make any sense at all. So you put $50,000 into a mount system for a new home, and you only use 10% of it or less, probably about 1% on the first year. And so why would we do that? It doesn't make any sense at all. I mean, at the very least, build half of that much and then build the other half 20 years down the road. But we don't think that way either. But you can dig in. I bet you dig into my system is 50 years old, on the far reaches, it probably has never seen a drop of water, I would guess. I have never done that, but I'm curious enough to do it when the weather turns better. Okay, so here you are. You're using gravity distribution. You're using very little water out of or very little of the infiltrative surface by gravity. There's just no way to get. You can do what you want to put a dosing in there, or a gravity dosing system, or a bridle header, or a distribution box. Anything you do is still just going to see a trickle of water going into it. You're not going to accomplish gravity. So pressure distribution gives you use of the entire infiltrative surface from day one. Now, if we really carried this, we did enough research, and I don't know how you do that, to carry this to the nth degree, we could probably have infiltrative systems 10 to 25% the size that we build today. You know, if we used equal distribution, they may never fail, but we don't. So how do we do that? Time dosing is one option, and we've got these are older timers, but you set the pump run time. You use a pump, number one, to dose them, and then you use time dosing to control the amount of time the pump operates. So typical setting on these in our mound systems and my designs have been 1 minute every hour. So every hour the pump kicks on for a minute, and it fills the pipe in the dosing field, and then that pipe drains out. You know, it cuts off. So 60 seconds out of every hour. So we use time dosing to do that. Set the timer in the pump in the tank, controls the time the pump runs when it's on, and the time it waits between doses when it's off. So those two settings are on these old timers. Today we got MVP panels that go in, little digital monitors, or that have that and a whole lot of other bells and whistles. Mike will tell you more about that. So we spread both the hydraulic loading and the organic loading in the wastewater. You got dissolved organic food source in organics in the wastewater, and you are spreading both that organic food source and application out over as much of the 24-hour day as you can design for, over a longer periods of time. So the other floats are, you get warnings with time dosing. It will only put, let's say, we set them for maybe 300, 350 gallons per day. So that at the most, if it kicked on every hour for so many hours throughout the day, it would deliver 300, maybe 300 or 400 gallons for the day. It won't deliver any more than that out to the drain field. So if the toilet starts running at a gallon per minute, it'll set off a high water alarm, because you're storing water in the tank, and the high water alarm will go off because the pump's not putting that much into the drain field. So and the other benefit is microdosing. So you're taking the daily water flow that goes up in the morning, 6 to 9 in the morning, comes back down during the day, and then goes up again in the evening, and then pretty well shuts down. You know, the flow is very little in the early morning hours, so, or the midnight to 6 a.m. hours. So now imagine, here's what we're trying to accomplish with small doses. Imagine the grains of soils in a dispersal area as being a media in a sand filter, or some other kind of geotextile filter, or any other kind of media, peat filters, foam cubes, anything else. The soil bacteria attach themselves to the soil surface. We feed them with wastewater so they grow and they multiply. They devour each other when the food source dries up. During periods of not very little use, they outgrow the food source, so they start cannibalizing each other. So they sort of self-manage themselves. The whole principle of activated sludge systems at treatment plants. They devour each other, especially extended air systems, what they're called extended air. But they need air to maintain the population of bacteria. They need a food source and air. So this is a saying, a soil grain, or media in a filter, or anything else. You don't want to flood and drown out the bacteria which are attached to the surface. So you don't want to fill all the pore spaces in the soil with water, because you get anaerobic conditions, and then you get the buildup of this black sludge that will seal off the soil eventually. So this is out of the Small and Decentralized Wastewater Management Systems book by Kreitzen Shabanigas, or whatever his name. I can never pronounce it. George T. anyway. Anyway, this is an illustration. At 1 dose per day, you just flood everything out. With 4 doses a day, you flood out most of the pore spaces, but you still have a little bit of entrained air. With 24 doses a day or smaller doses, you just get a little bit of water going down through the soil or the media slowly, and as it passes slowly, in these kind of cases, it rushes through the pores. In these kind of cases, it flows over the surface of the soil grains where the bacteria are, so you get better treatment when you use these small dosings, i.e. film flow or microdosing. So the challenge is too much water and too much food will generate anaerobic, saturated conditions, anaerobic conditions, and a buildup of the slime mat that clogs soils. Just the right loading will maintain aerobic treatment inside of here, inside the soils, inside the media, in any kind of pretreatment mechanism. So pressure distribution with small pipes and orifices provide equal distribution of food and wastewater. And again, there's that 10%. We try and keep the difference. Now, is that magic number? No, it's just a widely accepted number that when we went to equal distribution, somehow along the way, we picked the number out of the air and said, keep the distribution difference between the last orifice and the first orifice less than 10% difference. So that's become our standard of design and practice, was 10%. Compare that with gravity, which you have 0% equality. So I mean, it's like jumping from 0 to 90%. Like, you know, that's your comparison standard. But it is a good one. We use it. We use it in design. Gives us a design standard. So that provides uniform hydraulic loading and biological loading and better treatment. How do we accomplish this? And I'll go through these pretty fast, but we use a piping network and pressure distribution that minimizes the inequalities from one end of a lateral to the other, from one corner of a system to the other. And then we try and find the size of a pump to fit it. So this is a basically comparison of different size laterals or pipe with flow in them. Keep this in mind when you got this is 0 and that's 2 feet per second fluid velocity inside the pipe. If you map the flow coming up for 50 orifices in any pipe, if this is a 1-inch pipe, the velocity is going to be higher in the pipe, but the head loss is going to be much higher. So you get less orifices in a smaller pipe. If you use a 3/4-inch pipe, you eventually, to honor that 10%, you'd have to have a shorter lateral to keep equal distribution. If you got a 2-inch pipe here, you could put probably 30 or 40 of these together instead of 18 limit together with a bigger pipe to maintain equal distribution, but you would get very, very low velocities in that. So here's the bottom one here is a 2-inch pipe. So I can go out here 50 orifices and still got less than 2 feet per second. 2 feet per second is an engineering standard to try and keep solids moving in suspension and raw sewage. So I learned that in college 60 years ago. So it's 2 feet per second in gravity pipe is a design standard. In pressure distribution, you're never, with small diameter pipes, small orifices, you'll never reach that until you get way out here. If you use a 2-inch pipe, you never even get to 2 feet per second. But you're not dealing with raw sewage. You're dealing with only the solids that won't settle out in the septic tank after 4 or 5 days of residence time. So 4 or 5 days of residence time, that solid has to settle out of solution. So what comes out the other end is fine suspended solids that takes very little velocity to move them. So anyway, but with a smaller diameter, so you're kind of balancing this between good velocity. Here by about 12 orifices, you're up to 2 feet per second in a small diameter pipe. But so you will get some scouring velocity. So it's an engineering balance to try and figure that out. So in Verti-Grid layouts, you've got a manifold that can be any size you desire to make it. Could be, in small systems, we've been using a lot of 2-inch, and it's quite good. Keep in mind, when the water comes out from the pump, it enters here, and immediately there's a reduction in flow in the rest of the pipe. So head loss depends on velocity of flow inside the pipe. So if you've got a 2-inch pipe here, you lost 1/4 of the flow in the first lateral branch. The next lateral branch, you lost another 1/4 of the flow. So by the time you get down there, the flow in that section of pipe right there is only 1/4 of what the pump is pumping, because it's going out into all these. When you get into very large systems, an engineer should be involved in analyzing the hydraulics of this, and maybe in the very largest of systems, you want to use a manifold that is a 3 or 4-inch pipe. But you don't need to get carried away with the lateral size that way, or the manifold size. And by the way, contractor called me one time years ago, says, "Work, I looked all over, I can't find one of those manifolds you're talking about." Manifold is not pre-made, it's something you make out of PVC pipe, okay? It's just termed that, okay? So you're not gonna find those in the store, other than a length of PVC pipe. So again, for the purpose of Verti-Grid, 3 1/3 feet is the distance between orifices from module to module. They come with 1/8-inch orifices, but if you want to special order some with larger orifices, we can get them made that way. Just a matter of ask the manufacturer on an order to change the orifice size, but you will up the amount of flow, limit even shorter the amount of head loss, because this is always going to be a 1-inch pipe. So at least in this model, maybe someday we'll have a 1.25-inch model or something. But anyway, the orifice is always in the 6 o'clock position. So the manufacturer either drills it on the opposite side of the labeling on the pipe, or puts a mark on the fitting on the end here of the pipe. So that has to go up. These are installed in the vertical direction, but you could, if you messed with them, you can rotate that pipe. It probably, from 4 o'clock to 8 o'clock, it has no consequence. But if that gets rotated so the orifice is up against the fabric, it will inhibit the flow coming out of that orifice. So you don't want somebody messing with these and rotating them a lot. Okay, here's a table, for instance. Okay, so to go from 5 feet, this is orifice flow, 1/8-inch orifice, hole diameter. To go from 5 feet of design head, that 1/8-inch orifice will put out 0.41 gallons per minute. If you went to 6 feet of design head, in other words, you got some laterals that are 6 feet or a foot lower, so it's 6 feet now driving that flow, it's 0.45. So it's only 0.04 of a gallon per minute difference between in a foot of fall. It's another 0.04 of a gallon per minute if you go into 7 feet. So you have a lot of forgiveness in here when you use small diameters. So you don't have to be too worried about that. I particularly like suspending the pumps in pump vaults inside the tank to keep them up off the floor, because Mike and I have seen systems that had sludge buildup in the bottom of a pump tank with a pump sitting on the bottom, that where those solids it was a built-in float, and the solids built up to the point where it inhibited that float from turning the pump off. So, and it caused a backup and a failure of the system because the pump was running constantly. And you always have to have a means of flushing the lines. Early designs of pressure distribution systems did not have that. They had buried dead end pipes, and those are troublesome. So you have to have a flush valve on the end of the pipe. If you don't, after about anywhere from 6 to 12 years, that pipe, the ends of these laterals are going to build up solids, and that solids will eventually clog the orifice, the end orifice, and which will in turn clog the next one. Eventually, in the next one, you could get a slug of solids coming out of that. Somebody had a, who had a,
I'll show that video.
oh, you got that video? Mike's got that. These are, your imagination is only your limiting you to your use of these to work around other objects in the field. The tools are there. We kind of went through all of this. On larger systems, an engineer or somebody familiar with hydraulics should do actually a hydraulic analysis to size the manifolds and the feed pipe and the pumps. Okay, smaller systems, I've got a spreadsheet. If we had time, I would be able to show you how that works. How many of you have used or seen my spreadsheet? Wow, I thought more of you did. But anyway, it's an Excel spreadsheet. I'm willing to share that with anybody. Just give me a card or an email to send it to, and I can email it to you, or so you will have that. Just plug in a few numbers, and you can do an analysis of a pressure distribution system in 5 minutes. You can design your first one in 15. You can do probably your third and beyond in about 5. I do it on every system I design, and then print off the spreadsheets and send them in with our plans, so they know some thought's gone into it. We talked about this. The orifice here is always manufactured at 6 o'clock, and there's supposed to be a mark on the end of the pipe in the up position, so that down from the opposite side of that pipe is the orifice. So a quick and dirty without using a spreadsheet, if you want to, you can just look at that orifice discharge table, pick off size orifice you're using, pick off the number on that, multiply it times the number of orifices you've got in any one line or in your whole system, and I'd add a couple feet to it for head loss, but you could come up with a gallon per minute and take that flow per orifice by the number of orifices and give you a flow for your pump size, so you could give you, number one, your lateral discharge rate, and if you've got a complicated system with some long and short laterals, you may have to do it for each lateral. So if I've got 15 modules, orifices in one lateral, and I got 10 in another, the lateral discharge rate for 15 is one number, the lateral discharge rate for the next guy is 10, so that's a different number, so you may have to do that mathematically and add them up yourself. But basically, notice the difference. If you like 1/4-inch holes instead of 1/8-inch holes, and you put in the 1/8-inch hole discharge with the same head, 5 feet, it'll discharge 0.41 gallons per minute. A 1/4-inch hole, twice as large, discharges 4 times as much water. So be prepared, instead of a 50-gallon minute pump on any given system, if you say, I don't like 1/8-inch holes, I'll put in 1/4-inch, you better have a pump that's going to discharge 150, 200 gallons per minute. Do you have a question? Scratching your head. Okay. I don't like 100-gallon minute and more pumps, even on large systems. So, and I'm showing you this just to remind you, most of you, at least at Milan, understand pump curves, but the pump curve shows you how much any particular model pump will pump against whatever head. So the pump is always going to perform on the curve that fits that pump. So you have to select, calculate your TDH and your gallon per minute for any given system, and then look for a pump that those two numbers match. You can't, there's 50-gallon minute pumps and there's 50-gallon minute pumps, and they're not all the same. You can't just say, I need a 50-gallon minute pump. You need both a 50-gallon minute pump. At what pressure does it have to discharge at? So what's the head loss? TDH, total design head. So in the elevation, the TDH is the sum of elevation difference, friction loss in the pipe and fittings in the tank itself. There's a little bit of friction loss in the pipe in the tank, friction loss in the transport pipe or force main from here to the system, and then it is the residual head in the field. If the residual head, if you're designing to 5 feet, then you got to add that 5 feet to the TDH for the pump. So it's a summation of all that. So graphically, you got a pump down here pumping up to a drain field with distribution pipes, and it's the friction loss of the pipe here in the tank and fittings, the friction loss in the pipe itself, and a garden hose that's a ½ inch will give you, you've got to have more pressure at the head end to feed, you know, a certain gallon per minute at the far end than a 3/4 inch hose that for the same pressure at this end will deliver more up here because there's less friction loss in the pipe. So this depends on the pipe size and the pipe type, and then the residual head that you want the system to see when the water gets there. So, and elevation head difference. And I always estimate the low water level in the tank as the starting point, and this being the invert of the laterals as the ending point. This is a high head pump with a steep curve. Cutoff is 150 feet. I said I don't like these because solids can be sucked up and delivered to the drain field. So I never use this kind of a design anymore, even though most health departments would approve that and expect that as a standard. But here's a lower head single stage pump, which sets on normally on the bottom of a tank. And notice the cutoff head on these. Even the most powerful of those, the largest of those, the cutoff head's lower than 50 feet. And if any of you are interested in that spreadsheet, I can show you over lunch. But any questions? And the lunch is supposed to be here maybe in another 10 minutes or so. So they'll let us know. I would say that most of the systems I've designed using these, and it's about a dozen or 14 now, and is running with 1/8 holes again in a normal size system, is running from, sometimes you get away with a 30-gallon minute pump. We don't use a 40 very often. It's kind of an odd size. You either go 30 or jump to 50. So I don't know, why is that, Mylan? Are 40s readily available?
There's 40s
With the high head pumps. The high head pumps,
30-50.
turbine 30-50. And I use a lot of that high head pump, and so if a 30 doesn't work, I jump to a 50. But I rarely have ever gone on residential, needed a pump larger than 50. It's almost, that will do the trick. Half horse pump, 50 GPM, 115 volt. So you don't need a lot of extra power supply. So that works. And some other types of systems I've used, like 75-gallon minute pumps, you know, but other questions? Yeah, Maynard. Well, the way I do it, I use the Excel spreadsheet that I designed myself. And I take that and I plug in the lateral information, the number of holes per lateral, and it works not just on this, but in other pressure distributions. So I plug in the spacing of the laterals, the number of, I'll show it to you after at lunch if you want. The spacing of the lateral, or the holes, the size of the holes, the number of holes per lateral, the what? Oh, sorry. And do a lateral analysis, and it tells me when I'm exceeding 10% how many holes, orifices I use. And then I go through and I plug in the head loss information, the fittings and the size of the discharge plumbing in the tank, the size of the force main, the length of the force main, type of material, all of that, put in my residual head, gives me all the data I need, gallon per minute and TDH. And if I don't like the number, I go back and change something in my design. Oh,
Verti-Grid.
the Verti-Grid modules with an 1/8 inch orifice and the 1-inch pipe that's already installed, 18 is the limit in any one lateral.
Okay.
But you can, as long as you connect those with a manifold and you got a pump big enough, you can put in as many laterals as you want, but the limit should be 18, and you can put 18 one way and 18 the other way from a center manifold, or you could run that. You could put in 20 or 30 laterals if you want. You got a big enough manifold and a big enough pump.
Right?
If you want 500 square feet of bottom area for a house,
Okay.
that will take, divide that by 6. There's 6 square feet in each module. So divide that by 6 will give you the number of modules. The one in Grand Rapids was 900, the code said 900 square feet of, it was a sandy soil. So that seemed excessive to me. But anyway, that's what the code required. So 900 square feet divided by 6 was 150 modules. We're asking for the equivalent at the very least. Now, I came up with this analysis and recommendation based on the Michigan criteria, the Tyler table in the Michigan criteria, because I can go in the next county, and I can go in a county east of here. They want me to have 3,000 square feet of dispersal area. I mean, that's nope. Here's my take on this. The soil does the treatment with a Verti-Grid. This is a better dispersal means, not a treatment means. I can't tell you that there's research that tells me when I go out here 4 inches, its wastewater quality will be X number of parts per million BOD. I can't tell you that because I don't have that research. The research on this for sidewall area was comparing it to bottom area. That was 60 years ago, okay? And it would take us a long time to develop the kind of research to say with this, how big should these be in different soil types? So I'm trying to compare, start off with, you're gonna only require 500 or 600 square feet in a home system. We can give you this with, let's say, 75, 80, or 100 modules. 600 square feet, for instance, is 100 of these. So 600 square feet, you lay out a system with 100 modules in it. Okay, that's 600 square feet if you approve 1 per 1. 1 of these sidewall square feet per bottom area square feet. And we can put it in the same footprint that a bed is.